think you left an off right on the measuring gauge.
Hit that one, so I'm right above the indicators. Okay. Okay, so I think I talked yesterday briefly about the fact that we can use indicators to determine where the different pH is, and how you pick that. We talked about how you would use an indicator that is like plus or minus. If you look at the Ka value, you would want to turn that into a pKa, and then use the transition point where it transitions or changes color. You would use that to determine the pH range that you would want for that indicator. So if the pKa turns out to be like 4.5, you would want an indicator that would change somewhere in the range. Well, if you could find one at 4.5, that would be great, but you would want something in between 3.5 and 5.5. Okay.
So is an indicator just another acid or base?
An indicator is actually a buffer solution, and we're going to get into buffers. We haven't quite gotten to those yet. But what a buffer is, did we talk about it yet? I don't remember if we have or not. A buffer is either a weak acid or a weak base that, so, oh, please, no, not today. Please work for me. There, oh, good. Whew. So, so what a buffer is either a weak acid or a weak base. So let's say a weak acid. So a weak acid would be HA, right? That's an anion there. And then on the other part, it's going to have a conjugate that would be like maybe sodium, so a salt of that anion. So you could have like acetic acid and have sodium acetate here. So, or you could have a weak base and the conjugate salt, you know, the conjugate cation from that, or the, not the cation, but there would be a salt of that on the other side. So we talked the other day about our salts that can turn into acids or bases. They're acidic salts or basic salts. That feeds into this as well. So once we hit buffers, indicator is actually a buffer that exists. And that transition period where it's buffering, you end up with a color change. All right, so I think we did this one in class the other day. So majority of the titrations, then you're going to be determining a solution concentration, volume, molar mass, or percent purity. So percent, like how much it ionized or how much of the material's in there. Regardless of whether it's an acid or a base, the total number of moles of hydrogen from the acid equals the number of moles of OH from the base at the equivalence point. So the equivalence point is where these two things, number of moles are important, number of moles of your H plus and number of moles of your OH are equal, okay? So any type of titration that you're working on, you really want to start with that balanced chemical equation, okay? And pretty much all of your equations are going to have monoprotic acids or bases. They're not going to throw a polyprotic at you. I would be very, very surprised. So the first step then, after you've got your balanced equation, usually involves figuring out the number of moles of the reactant, and then using that to figure out the number of moles of the second reactant that's consumed, figure out which one is in excess, and then calculate your pH based on that. Okay? So we didn't do, you don't have this one done, right? In your notes?
Yeah.
We do? Okay.
Yeah.
Okay, so we did do this one yesterday. So then when you calculate your solution volume, so if you didn't watch yesterday's video or you want to try this one again, your answer should be 0.188 molar H2SO4. So if you just want to have that down kind of as a review from yesterday. Did we do this one yesterday at all?
Yeah.
We did. Okay. So again, titration data, you're usually going to get that. And then you can also figure out volume of your base based on this information too. Now, this is a strong acid, strong base problem. So this works out pretty well, pretty easily. And then we talked, did we talk about acids and base indicators, or is this where we left off? Okay. All right, sorry about that. I guess you got a little review. So these titrations then, we're going to use an analysis. And this is what I was trying to talk about a few minutes ago, where I was talking about if we had a weak acid here, we would have its conjugate anion here. So this could end up forming and have that conjugate on the other side. And then a small amount of that indicator is in place, and it typically will have some sort of color change that occurs when it flips from that acid to the base situation. And that happens for different things at different pHs. And so you could end up getting different color changes based on that. So like methyl violet, this is where its color range is, and these are going to be its different colors. And thymo blue, these would be its ranges. And so if you were trying to find the pH of something, and you needed to know, where it was flipping, you would look at the Ka value and try to match that up. So if you had a Ka value in here of like 1.7, this would probably be a good indicator to use. Yeah.
So is an indicator basically just an ion that takes the cation or the anion away from the acid and then turns it into a salt?
Yeah, so it'll take this hydrogen here, add OH to it, okay? So like this one would take water here and form this, and then that would be leaving this behind. And so in the base form here, it's one color, and then the acid form, it's a different color. And so since your eyes can detect that color change, that allows you to be able to tell when it's changed within that when that equilibrium. Remember, the equilibrium point is where your H plus and your OH minus, the moles. I guess I shouldn't use brackets because this is actually moles. It's not molarity. So the moles of this equal the moles of this. You're at equilibrium. And that changes based on how many hydrogen ions this weak acid gives up. Some of them give up a lot more than others. And so this period where, when you've got the amount equal to this, so if we're dumping in like some OH ions here from a base, okay, and that hydrogen's going with that to form water on the other side, then it's going to take a lot longer for the moles of this to equal the moles of this, because if this doesn't give off a lot of hydrogens, it's going to take a while for that to happen. So there's a variety of different, I mean, there's a lot more indicators than just these. These are just a listing of some of them, but you can see that they have quite the range here. Phenolphthalein is one that we commonly will use in here because it does change. It does end up with a color change. You're actually not even going to use an indicator in the lab that you're working with. You're going to use pH meters. So you'll be taking the pH, and what you're looking for in that lab that you're working with is the point where this increases the pH, and then eventually you get to a point where it goes straight up and then it'll level off here. You're looking for that straight up section here, and that's what that derivative helps you find, is where that straight up section was. And so you'll be using pH meters to figure it out and then do some math.
You get to see a color change?
No, you don't get to see a color change. I know. Disappointing. I get it. You'll get it. I know. I mean, I guess we could probably, I mean, you could put some phenolphthalein in the end and see it go from clear to that. And you can go, ooh, ah, I can pull some out if you want. Just turns hot pink. So indicator change that you can see, again, if we look, we typically will look for Ka values that are plus or minus 1. So the concentration values would be plus or minus, in the tens range. So indicator transition point here, pH will equal your pKa, and that's where you end up with this kind of intermediate state. So again, you can look at these titration curves. This titration curve here, when your pH starts out here, like between 0 and 7, somewhere in this like 2, 4, 6 range, that means that you're starting out with a weak acid, okay? And if this ends up going up to a 14 here, you've ended up titrating that weak acid with a strong base. Here we're titrating with a weak base. We know that it's a weak base because the pH is starting out between 7 and 14. It's in this kind of intermediate range, so that means that it's weak. If it was a strong base, it would start out up here, somewhere in this general vicinity. Okay, we ended up titrating that with a strong acid, and we know that it's a strong acid because your pH in the end ends up down here right by 0. So you can look at these pH curves. I didn't even read the information down here, actually, when I was going through this with you, and I see that it says that down here. But I got all of that information just from looking at the graph. The equivalence point is where, do you see this straight line that occurs here? That's your equivalence point. And you will find however many milliliters you have at that point. That is how the volume of the HCl that it took to be able to get this to come out. So if we knew the molarity of that HCl, we could actually tell how many milliliters we put in and be able to determine how many moles of hydrogen that is. So let's say that this was a 0.2 molar HCl here. This came out to be, let's say that that's like 22.5 milliliters, right? If I take that and I multiply that times my molarity after I turn this into liters, so 0.2 times 0.0225, that would equal the number of moles of H plus that I had added in there. And then, since that's at the equivalence point, we would know how many moles of weak base we started with. That makes sense? One of the other interesting things is that at this point here, where these are equivalent, okay, that is how many milliliters it took. So if I want to know where it is at the half equivalence, I would divide this by 2. So that would be 11.25. If I find 11.25 on my graph here, we call that then the half equivalence. Okay, at the half equivalence point, whatever the pH is for that, at the half equivalence, the pH will equal your pKa for that material. So let's say that this was our halfway point here. Our pH is 9. So that would equal our pKa. And then we could go back and from that figure out what our Ka is for this. Because if you have pKa, right, if this is 9, if pH equals 9, then that's going to equal your pKa. And if I take 10 to the negative pKa, that will equal my Ka value. So here is a weak acid, weak base. We were talking about this, I think, this morning, weak acids and weak bases, how we don't know exactly where they're going to end up with their equivalence point. When you have a strong acid, strong base, the equivalence point is 7 for your pH. But with weak acid, weak base, you have to look at the Ka and the Kb values. And whichever one is greater, and yeah, so then it'll determine whether it's an acid or a base at that point, and then you can try to derive that from that information. You're not going to have to do that, okay? You need to be able to work with strong acids, strong bases together, a weak acid and a strong base, and a weak base and a strong acid, okay? So don't worry about anything like this. You're not going to get anything like that thrown at you. All right. So 8 acid-base indicators are listed on this page over here. I guess there's more than 8. I think there's more than 8 there. Okay. So we have those indicators there. Okay. Oh, display in orange. Okay. So we got display in orange at their transition points. Identify which one of those has a Ka that is 5 times 10 to the negative 8. Okay. So let's see which 8 we're talking about here. So orange would be red and yellow, right? So we've got that one. We've got this one, this one. We have this one. That's 4. This is 5, 6, 7. I must have missed one. What is amber? Is that the one I'm missing? Huh? Maybe. Yeah, we'll call that one.
Well, if you have 7, then there's your 8.
Yeah, that's what I was trying to find the 8th. I think that's probably it, but I'm not circling it with great confidence. Well, it's not the answer, so it doesn't really. Will be. Process of elimination, the rest of these are green. Yeah, so we're gonna go with that one. All right. So if I want to look at this, I want to look at my pKa value, right? Because we said that pKa, we wanted to have that plus or minus 1, and with the pHs. Okay, so they've got pHs here. We know that our pKa value then will be negative log of this. So pKa equals the negative log of the Ka value, which is 5 times 10 to the minus 8. So when I do that, I end up with a pKa of 7.3. So I'm looking for something that's in the range of a pH that's close to 7.3. So if you can find a pKa that's very close to that transition point, or that has a pH that's close to that pKa value, that's what you want. So go back up. 7.3 is the number we are looking for. So we can get rid of this guy because he's nowhere near that. Okay, 7.3 is what we're looking for. So this one might be it. Might be this one. If we knew for sure that that was, yeah, I don't know what amber is. Amber, waves of grain. So it must be yellow, right? Because grain is yellow.
Look it out.
I think it's yellow. We're going to go yellow. There's a song, right? Amber waves of green.
Yeah, it's a yellowy color.
Okay, so that works out.
Yeah, it's yellow.
The mine thing is right now.
It's gotta be complicated.
So we're going to get rid of these because these aren't anywhere near 7.3. No 7.3s here. No 7.3 here. So that's really going to leave us with this guy, right? Or this guy.
Wouldn't it be the red to amber because it's a smaller window?
Yeah, either one I guess would be fine. They said phenol red in the answer key, but yeah, I think either one of those would be fine. I didn't originally identify amber with yellow, but now that I think about it, I'm like, yeah, that works out. So yeah, either one of those would be fine to grab off of the shelf in the back. Assuming we have them. I don't even know which ones we have back there. So I know we got phenolphthalein and we've got universal indicator. Those are the ones I know for sure. The other ones I keep back there, they're mostly for biology folk. Okay, acid-base curve titrations is where I need to be right now. Here we go. Okay, so we're going to look at these more kind of detailed things and what's going on with them. Those are called titration curves. That's what you're going to create in your lab when you come in next, okay? And we can do a plot of the pH. A lot of times, like if we would have done a titration in chemistry, which unfortunately we didn't get a chance to last year, if we would have done one of those, there would have been an indicator in there that would have told you where that transition was occurring, okay? What we use this year is a little bit more complex than that. The indicator requires your eye to be able to sense when that transition has happened, okay? And everybody's eyes have different abilities to sense things. Yeah.
So, I just want to make sure. So the x-axis is like whatever's in the long burette that we're slowly putting into the glass.
Yep. This is your titrant, T-I-T, and it's milliliters of that. And then your pH is along the side. Okay. So, like I said, when we do this in regular chem, we look at this and we don't really plot pH so much. I mean, you can like take different samples of it and try to figure out, oh, well, this is where it's going straight up because I know that the strong acid, strong base, and that's where the equivalence point was. And then you can kind of go off to the side because you know what the pH of that strong base would be in the end. But this year, what we do is we actually use pH probes. So you're going to be starting out with 0 milliliters of this, and you'll have an actual pH in your beaker. And it's going to be a weak acid that you're starting with here, and you're going to be titrating that with sodium hydroxide. And I believe it's 0.5 molar sodium hydroxide. I think that's what I've got out here to pull for the lab. I can't even find my sheets anymore. Yeah, 0.5 molar NaOH. So you can kind of see the setup on the lab that you have here when you come into class. Let me pull up that diagram. Oops, that's not the diagram. Oh, that's over here. That's why. Okay. Come on. Mouse. There we go. Page up. So this is the setup. You'll have 2 different burettes set up. This one will be your acid burette. So you will start out with your weak acid in here. And the reason why we put that into a burette is because we want you to be able to accurately know the volume of that. Okay. So I'm going to ask you to put in burette, blah, blah, blah. Dispense 30 mils of the unknown acid. Now, if you get 29.95 mils in there, that's okay, but you need to make sure that you document exactly with how much you're starting with, because you've got to know how many moles of that you're working with. Okay, and then so once you have that in that container in the flask, and you're going to be working with a flask here, a lot of times if you do titrations, you will actually use a flask here instead of a beaker. Okay, but you're going to use a beaker, and I'll explain to you why in just a second. The reason why you typically will use a flask here is because you have an indicator in here and you want to swirl that. And a flask allows you to swirl without having it slop out the sides. Okay, but what you're going to be working with is you're going to have your base set up here, and make sure that you have these labels done correct. Like, put the base in this one, put the acid in this one, and use these labels. And I use red for acid and blue for base to try to, like, this is my base. Okay, you are going to have another clamp here that the arrow is kind of covering up, but that arrow, this is going to be a clamp here, and that's going to be holding your pH probe in position, and that's going to be down in here. The reason why this is sitting on here isn't for heat. Do not turn the heat on. What you're using this for is the magnetic stir plate in there. So instead of swirling this, you're going to have a bead that's going to go around inside there that's going to stir it for you. And that's going to make sure that when you're adding in this base, that it's getting distributed properly in there so that the pH probe picks up on the proper pH value. The reason why we end up using a beaker for this instead of a flask is because you're not stirring it, the thing is, and then that gives it enough room for your burette to be down in there and the pH probe. If you have this in a flask, the neck of the flask gets kind of tight with all of that stuff in there. And so it makes it easier if you have this going in a beaker. But normally when you do titrations, if you're using an indicator, you will be using a flask. So I just want to tell you that, so if you end up doing these in college or somewhere along the line, that would be a very typical thing that you would experience. Okay, so base burette, acid burette, they are coded here. Make sure that you follow the things. I try to make sure that we use the clamps that are already pre-labeled for you. You have your pH probe here that's hooked up into your LabQuest, and then your LabQuest is hooked up into your computer, and you've got vernier probe wear going on there. Then in the Logger Pro, you're going to set this up. You're going to select experiment, calibrate that pH meter. We did calibration when we were doing the yeah, didn't we did that before you guys left, right? Before you went on winter hiatus or whatever it was.
I think it was Thanksgiving.
Yeah. Crazy time this year. Okay, so then you do your data selection. You're going to start your magnetic stir. Okay, so make sure that you have this set up properly. You want units to be in milliliters. That's going to make a difference with stuff. Then you start collecting, and you're going to press keep every time you add some of that base in. Okay, and the initial part, you're going to add about 1 ml of the base into the acid. Wait until that pH is kind of stabilized. Hit keep. Put in your new volume, how much of the base you've added. So you'll start with 0 and you're going to go up from there. Okay, now repeat step 6, going by half mils when you get about 3 mils in. So about 3 mils, you're going to want to go about ½ a mil. And then when you see that thing starting to go like straight up and down, you're going to want to go even less than ½ a mil. Okay, so around the pH of 7, you just keep doing that, keep until you get a pH of around 12. Okay, you need to save your lab. This is not Google. Okay, Vernier does not automatically save for you. You have to do this yourself. Make sure that you print off enough copies for all of the people in your lab group, which will be either hopefully 2 or 3. And then I want a copy of that with the lab. I have that video that you need to listen to so that she shows you how to get these tables set up. This may be a 2-day lab in here, okay? So what I'm going to do is I'm going to set up 4 tables, 2 for A day, 2 for B day. And then that way, if you need to leave your stuff and come back to it the next day, or 2 days from whatever, I see you next, then you can come back. And if you've saved your lab, everything should be fine. Okay? If you goof it, you got to start over. And then I've got different calculations and that sort of thing that you have to do after that for the lab. Okay, but you should start out with a pH value. Since we're starting out with a strong acid, you should start out with a pH that's, no, we're starting out with weak acid. I'm sorry, weak acid. So we're using, well, I can't tell you what you're using because you have to try to figure that out as part of the lab. So I'm going to tell you that. You're starting with weak acid, so the pH is going to be down in here. If we were starting with a strong acid, it would be down here, okay? When you titrate that, then you're going to end up with a straight line at some point, and then it'll level off like this.
Well, I guess you know it's not HL.
No, no, God, no. Oh my God, no. No, that's scary. Yeah. Yeah, Lippy doesn't like to do scary things. She's likes to err on the side of safety. So, that's analyzing it. Again, equivalence point is that straight up spot that you're looking for where things are going straight up and down. That's going to be your equivalence point. The other point that is important, so you figure out what milliliters this is. So this was 25 mils here. Half of 25 is 12 and a half. If we go to 12 and a half here, that's your half equivalence point. If you know the pH of that, then you know the pH at the half equivalence point equals what? pH at half EQ equals what?
Twice
the pKa. And if you know the pKa, you can easily get to the Ka. Because 10 to the negative pKa gives you Ka.
So are we trying to find Ka so that it'll tell us what acid it is?
Yep. So you're going to go, once you've figured out what the Ka value is, then you can go to a chart of acids, look at that chart, and hopefully come up with the right one.
I thought you'd give us a chart of Kb values.
That would be mean. Typically, they're published as Ka values. Like if you look up, even like ammonia is usually, they give you a Ka value of it, and then you have to be able to derive a Kb from it. Yeah, so even, well, I guess they did give you a KBs down here for these, for this chart. They were nice. But here, they give you Ka values for these. See, there's ammonium here. That's times 10 to the negative 10. So these would all end up, you know, forming bases, but. Anyway. All right, so titration curve then, if we had 25 ml solution of HCl with an AOH, that's going to be shown here. Okay, we know that we started with a strong acid because the pH is between 0 and 2. Typically, if you're between 0 and 2, you are going to end up with you'll end up with a strong acid. Your equivalence point here is at 7, so we know that we had a strong acid, strong base, or we have a pretty good indication of that since this was a strong acid already. We've analyzed that. This is between 12 and 14, so typically that's where your strong bases will come in at. And we had an equivalence point of 7, so we would be pretty confident in saying that this is a strong acid, strong base titration here. Okay, because this acid is strong, the H plus concentration tends to start out very low for the pH. The titration then proceeds. You're going to add in that because you've got excess acid here. But when we get to this point, now we're going to have excess hydroxide ions. And so that's going to end up being excess base at that point. So the pH approximately halfway to the equivalence point. If we know that, then once we've been adding in, sorry, and calculate that pH. And before the reaction, you can subtract the lesser concentration from the greater, and you can figure out which ion is in excess. So then, if we're over here, so we get into some calculations, a few calculations before we have to leave for the day. All right, so calculate the pH of the solution produced in the reaction flask during a titration following the addition of 12.5 mils of 0.1 molar NaOH to 25 mils of 0.1 molar HCl. Okay, so if I start out with my equation here, I have H plus. This is from my HCl here, from HCl. And I'm going to add in my OH minus, and that is from my NaOH. And that's going to produce on the other side water. And it would also produce sodium chloride. They're all aqueous. Essentially, this is my net ionic equation. Okay. Okay, so if I started out, I need to calculate how many moles of my HCl I have and how many moles of my OH I have. So when you are dealing with a strong acid or a strong base, you're in the land of moles. You've got to use your stoichiometry. Okay, so I'm going to multiply 0.025 times 0.1, and that's going to give me my moles of H plus ions. Okay, so that gives me 0.0025 moles of H plus. I'm going to put BCA over here just to help me remember that I am dealing with moles in here. Okay, if I'm in ice, then I deal with molarity. Then I'm going to take this value, and I'm going to calculate my moles of OH ions. So I'm going to take 0.0125 times 0.1. And that's going to tell me my moles of hydroxide ions. So 0.00125. So which is going to be my limiting reactant, my hydroxide or my hydrogen? My hydroxide. I have less of this than I do this. So I'm going to use all of this up, having none remain. And I'm going to use up 0.00125 of this, and I'm going to have 0.00125 remaining. Okay, now these are moles. Okay, if I want to calculate pH, what do I have to have? Nope. Negative log of what?
Okay.
Nope.
Okay.
Negative log
Liters.
Of what?
of KA.
No, not Ka.
Is it liters?
Nope. What is pH? You did this last year. pH equals the negative log of what? What does H stand for? Hydrogen ion, right. So it's the negative log of the hydrogen concentration is what your pH is. So we need to figure out hydrogen concentration. We don't have hydrogen concentration over here. We have hydrogen what? Moles. So how do I get from moles to concentration? What unit is concentration given in? Molarity. So molarity equals what?
Moles over liters.
Right. Moles over liters. So I have my moles here. 0.00125. How do I get my liters? So what are my liters? How many liters do I have? 0.025. That's my hydrogen. Yep, that's my HCl. But what did I do? I ended up doing what with these two things? I mixed them together, didn't I? So I have 25 mils of this, and I have 12.5 mils of this. So what is my value down here? Not 275. 12.5 and 25 is? Yes. And that's going to equal my molarity. I'm still not to pH, y'all. So my molarity, when I divide these out, is 0.0333. That's my molarity of H+. But they didn't ask that. They want to know my pH. Negative log of this value, then, will give me pH at this point.
So I got a question. Since there is a strong acid and base, right? Does it like exponentially get smaller just because of the amount of milliliters? Like
Smaller.
like because it's a strong acid and strong base, right? So the equivalence point would be 7, but there's double the amount of HCl. So, and it doesn't like, obviously 3.5 would be half of 7, so does it like exponentially get like more acidic?
It gets less acidic as we add more base in. So pH is increasing here.
No, but we have more acid here. We have 25 milliliters of HCl compared to half that for the base.
Okay. So I say the question again.
So, are we, okay, so wait, did we just find the half equivalence?
Yep, that's where we're at, was half equivalence.
Okay,
We didn't find it. We wouldn't know that that's the half equivalence until we run the actual, like, whole, unless, you know, if we were given the Ka. If you're given the Ka, then you might know it. But you wouldn't know that this is half equivalence until you know where the equivalence is. That makes sense?
Yeah, it makes sense now that I'm looking at
The graph. All right, so keep working in your packets. if you want, you can try to do the next couple problems on here, like at the equivalence point, and then the fourth one, but don't try to start the weak acid strong base
Report to
yet.
the AP office. Kendall Shaw to the AP office. Kendall Shaw to the AP office. Thank you.